Here we go. Chapter 1, Matter, Measurement, and Problem Solving. If we polled the room and asked, what do you think the most important idea in all of human knowledge is, we'd probably get a lot of answers. If you asked other instructors in other classrooms, they would probably have different answers. In the chemistry world, in the scientific world, it might be this. The properties of matter are determined by the properties of the molecules and atoms, the pieces that make up matter. The smallest little bits of matter the way that the submicroscopic world, the world that we can't possibly imagine, at least not very accurately, the way that those small particles interact with each other determines how our big world interacts, where they provide some information about how the big world interacts. The way that the atoms and molecules, the smallest little bits and pieces, those things determine how matter behaves, and if those things change, then the matter also changes. The way that the world that we observe also changes. So this gives us an unprecedented level of control over that matter, or at least understanding of that matter. So what are atoms? Atoms are submicroscopic particles, smaller than you can see on a microscope, at least a normal one, that constitute our fundamental building blocks. These are the one-by-one Lego brick of the universe. They are very, very small. Free atoms are rare in nature. It's usually not just one thing from the periodic table showing up by itself in nature. It's usually joined with a couple of other things. And when atoms join together, multiple atoms together equals molecule. So if you stack a couple of these little Lego blocks together, you get a molecule. And water forms molecules, is made up of molecules. We've got an oxygen atom, usually represented by our red sphere, and we've got two hydrogen atoms represented by those white spheres. So two hydrogens, one oxygen, put them together, and we get water. And all water is going to have this same chemical composition. It's always going to be two hydrogens, one oxygen. And the properties of the water molecule, the way that these little pieces interact with each other and behave, determines how the water that we observe, that we drink, that we sweat, that we do other things with, like bath and shower, it determines how those things behave. If we make a small change with a molecule, if you change the formula, it can result in a big difference in the properties. So for example, we've got a water molecule here on the left. We drink water, hopefully. Two hydrogens, one oxygen. If you add another oxygen, it's hydrogen peroxide. It's hydrogen, two oxygens, and then another hydrogen. Hydrogen peroxide you should not be drinking. Hydrogen peroxide is a bleaching agent. I don't know if it's used for hair, but it's often used for teeth. So like teeth whitening strips usually have hydrogen peroxide or something like it in them. You should not be drinking hydrogen peroxide. There's even a joke about a chemist walks into a bar and says, I'll have H2O. The bartender comes over, sets down a glass of water. He drinks it. He's fine. Another guy comes in and says, I'll have H2O too. And the bartender comes over, sets his drink down. The guy drinks it, and he dies. Because he ordered hydrogen peroxide, H2O2, instead of water. So part of the goal of chemistry is that we want to know how the substances around us behave, and we do that by figuring out how the little tiny building block pieces behave. So we will be looking at the behavior of atoms and molecules. For example, two similar compounds, graphite, like you have lead in your pencil, if you've got a mechanical pencil especially, versus diamonds. They're both just carbon. Graphite's just carbon, diamond's just carbon. But the way that they interact, the way that they're layered, the way that they're bonded together determines whether it's graphite, which is super cheap, or diamonds, which are artificially very expensive. So those little differences make a big difference, at least to us. We'll talk briefly about the scientific method now. Hopefully, you learned about the scientific method, but I know the curriculum has changed a lot since I was in school. So the scientific method, this is a process for understanding nature, and it includes a couple of steps. This is the brief summary of the key steps. Key characteristics. We have observation, formulation of hypotheses, educated guesses. We've got experiments, and then formulation of laws and theories. We don't always come up with laws and theories, but sometimes we come up with things that are close to laws and theories. So the first step of scientific method, observations. Observations are things that we observe. We would also call them data, information that we collect about the world. So observations, information we collect. Sometimes, especially in the science world, we collect that data with numbers, or we collect that data with physically writing stuff down. Other times in our daily lives, it's probably just stuff that we see and we store it in our memory and maybe we remember it later. One example of data, Antoine Lavoisier, it's a painting of him. In the late 1700s, he made some careful measurements. He took this apparatus here and he put stuff in it. It's a sealed glass apparatus. He put stuff in it, he lit it on fire, he closed the container, and then he did measurements. He just burned stuff and then recorded before and after. He noticed that the mass measurements, the mass of the objects before and after burning them, was the same. There's no change in the total mass before burning and after burning. That's part of why he had the closed container, so he could make sure everything was captured. So those were some observations that he had. He burned something, the mass didn't change. It's the same mass before and after, burning, non-burning. So those are some observations that he noticed. And oftentimes, sometimes, these observations, these things that we notice with our eyes, with our instruments, with our other things, can lead us to formulate a hypothesis. A hypothesis is a tentative interpretation or explanation of the observations, or an educated guess. To explain the observations. Why are we seeing what we're seeing? For example, if we get up every morning and our favorite cereal bowl and spoon has been set out for us because we have cereal in the morning in this hypothetical. If there's a bowl and a spoon and our favorite cereal right next to it every single morning, there are a couple of possible explanations. If we live alone, maybe we're sleepwalking and getting ready for the morning in our sleep. Maybe somebody's breaking into our house and setting out our bowl and spoon and cereal. We've got a stalker. Maybe we have carbon monoxide poisoning and we just don't remember that we set it out the night before. If we don't live alone, maybe somebody special to us, maybe somebody who cares about us, like our dog, set out our bowl and cereal and Reese's Puffs, or whatever cereal you enjoy. So that would be a hypothesis. Guess, just why are the things the way they are? It doesn't have to be right. Lavoisier, the guy that burned stuff in the previous slide, he explained his observations of combustion. His hypothesis was that when a substance burns, it combines with a component of air. That's part of the combustion process. It's just rearranging its composition. A good hypothesis is falsifiable. So if I say there's a magical man that lives in my house who sets out my bowl and cereal and spoon, but he's invisible and he does it just sometime, that's not a very good hypothesis because I can't necessarily prove that there's not a magic man in my house who does that for me. So a good hypothesis, we would have to be able to set out a camera and catch it on footage. Did the magic man show up and do it or not? So a good hypothesis is falsifiable, can be proven false. If you can't prove a hypothesis wrong, That makes it a lot harder to provide evidence that it's not wrong. Generally, we don't actually consider things proven correct, but we can be right or wrong. And if we can prove it's wrong and it's not wrong, that's a good sign that it's right. So those are our hypotheses. The way that we prove things wrong is with experiments. Experiments are ideally highly controlled. So we control as much as possible. We limit the variables. We try to test just one thing. These are designed to generate some more observations. So we'll observe what happened during our experiment. And the more controlled it is, the more that we just checked one variable, the more we have an idea of whether that one variable was responsible. So I've been on a sleep kick recently because of one of my, and by sleep kick, I don't mean I've just been doing a lot of sleeping recently, although that's also somewhat true. But I had a student in my Chem 1 last semester who's like addicted to like, not sleep, but like, he's like hyper-focused on sleep. That's his special interest. And so he was telling me, Mr. K, you got to be on magnesium. You got to be taking, low-dose melatonin. You got to be getting fresh air. It's got to be it's got to be really cold in your room. All these sorts of things. And so I was like, all right, whatever, dude. And then later in the semester, I was like, you know what? I'm going to give it a shot. Let's try it. Let's try the magnesium. Let's try the low-dose melatonin. Let's try the fresh air. So I got some magnesium. I got some melatonin. I'm opening the window to make sure I'm getting fresh air and my CO2 levels aren't elevated. I did all three of those things at the same time. I don't know if any of them are helping, and I'm not really collecting good data about whether they are helping. That's not a good experiment. I don't know if I'm wasting my money on magnesium glycinate, thank you Costco, or low-dose melatonin, also thank you Costco, or if the cold air, the fresh air is just a hoax. It's probably not, that's probably real. Really bad experiment. Would not submit it. So ideally, right, for my getting better at sleeping, I would try, let's just add the magnesium. Let's make sure we're going to bed at the same time every night. Let's make sure that we're equally cozy every night. We got the temperature locked in, right? There's lots of things that we can do to control that process, and then I know, hey, maybe the magnesium is helping, maybe it's not. If it's not helping, throw it out, try something else. Or maybe we also add the low-dose melatonin on top. We test one thing at a time rather than just throw the kitchen sink at it and see if everything works. If the results of the experiment, we should get some results from our experiment. If you're not getting results, positive or negative, sometimes the results are just, it didn't work. And that is also a valid result. We can modify or discard our hypothesis. And then, if we get enough of these results, we can come up with a scientific law or a theory that we'll talk about next. So our scientific law is a brief statement. It summarizes past observations, and it can help predict future ones. If X, then Y. For example, if I don't put gas in my car, then my car will eventually stop running. It doesn't explain why it's happening. It just says, if I don't put gas in my car, then it won't run. If I don't eat food, then I will die. Doesn't say why. So the law of conservation of mass, this is something that Antoine Lavoisier contributed to. In a chemical reaction, matter is neither created nor destroyed. So before he burned the stuff in his little apparatus, and after he burned the stuff, the mass was the same. We weren't creating new matter, the mass didn't go up. We weren't destroying matter, the mass didn't go down. We were just jumbling it around, rearranging it. Scientific laws can also be subject to experiments. They can either support them or prove them wrong. For a lot of the chemistry stuff that we're going to learn, it's pretty hard fact at this point. Our scientific laws have gone through a lot of testing and rigor. For some other fields, I think astronomy has some where they're like, we don't know if this is true or not. And there's people on one camp and people in another camp. So it's a little bit more contentious. Some of the laws, they're like, no, that's not right. Other people, yeah, it's right, you're wrong. There's a little bit more contention. The stuff we're learning in Gen Chem, it's pretty much all hard fact. Unlike state laws, or federal laws, you cannot just choose to violate a scientific law. It doesn't work that way. You can't break them. You can't break scientific laws. It's true if, then. State laws, federal laws, of course, you can choose to break. Generally, not the best idea. But you make your own decisions. You can also, if you get one or more well-established hypotheses, you might come up with a theory. Theories are generally a model for the way nature is, why it is, what it is, but also why. So theories, in addition to explaining what happens, explains why it happens. For example, John Dalton's atomic theory, he lived about the same time as Lavoisier. His atomic theory explained the law of conservation of mass, so it added some extra information by proposing that matter is composed of small indestructible particles called atoms, those little one-by-one building blocks we talked about earlier. And since you just rearrange those, the total of mass remains the same. This is sort of like I grew up playing with Legos, Duplos, and you would build stuff. We just had the big boxes. You'd build something, and then little brother, little sister comes along and smashes it because they're a toddler. And then, oh no, my Lego is broken. But all the pieces are still there, right? All the pieces still go into the box at the end of the day. I could bring those pieces out and I could build the same thing again the next day. I would still have the same amount of pieces in the box. They haven't eaten the Lego. They haven't fundamentally destroyed the Lego. New Lego blocks have not been created. It's the same blocks, just rearranged. So the atomic theory is sort of the same way. So our difference between laws and theories explain why. A lot of the time we can't conclusively prove something because there is potential that we could override something. Again, most of the stuff we talk about in this class, the way it is the way it is. And here's a chart of what the scientific method might look like. You would start at observations. If you get enough observations, you might go directly to making a scientific law. Otherwise, you're coming up with a hypothesis. It could lead to theories. It could go through experiments. You test those hypotheses with experiments. It either confirms or revises the hypothesis, and you repeat the cycle, and then maybe at some point it spits out and becomes a theory or it becomes a law. Questions so far? For the most part, we don't explicitly use the scientific method. Like most researchers, I think, are not sitting in their office like, all right, step one, we got to come up with some observations. It's just like we sort of operate this way. So we come up with some observations, we notice some things, and then we come up with, why is that thing the way it is? A lot of us probably do this too. And then we maybe do some tests. Why do I always break out when I use that one perfume? Why do I always get lots of compliments when I wear that one cologne? Well, we probably know why, right? There's something in the perfume that makes our skin itchy. It irritates our skin. Let's check the ingredient list. Let's check another product that has a similar set of ingredients. We can do some of that work. You probably do some of this stuff. Oh, I get really gassy and smell bad when I have milk, right? There's some things like that. We do a little bit of the scientific method by ourselves. Okay, which of these statements best describes the difference between a law and a theory? Is it A, a law is truth, a theory is mere speculation? Is it B, a law summarizes a series of related observations, a theory gives the underlying reasons for them? Is it C, a theory describes what nature does, a law describes why nature does it?
B.
It is B. Some of you might have guessed C because it does do this what-why difference. But the theory is what theory describes why. not Siri. It does sound like that, though, if I have a lisp. And a law describes what? Sometimes my iPad is like a little too helpful. So in C, we got them flipped, right? A theory describes why nature does something, and a law describes what nature does. So that's why you might have guessed C, but it is B. A law summarizes related observations, and our theory gives the reasons for those observations. Why did those observations happen? Why did what we saw happen? Okay. Matter. What is matter? Matter is anything that A, occupies space and has mass. Most of the stuff in this room is matter. Your textbook, if you have textbooks, your desk, your chair, your body, the air, all matter. They occupy space and they have mass. One particular instance of space, one piece of space, we could call a substance. Chemicals, substances, desks. A desk is a substance. Water is a substance. We can also classify matter based on its physical form, physical state, the states of matter, as well as its composition, what is in it. We also have this very corny shirt. You occupy space, you have mass, you matter. We're missing an R there, it's you are matter, but you do matter, you are important. I'm glad you're here. Okay, so classifying based on physical state, its form, as well as composition. We've got three states of matter that we're going to talk about. We are going to talk about solid, liquid, and gas. The state of matter changes from solid to liquid to gas with increasing temperature. If we have a little graph with just temperature as our axis, our lowest energy or lowest temperature phase of matter is our solid. If you heat something up from a solid, it becomes a liquid. If you heat something up from a liquid, eventually it becomes a gas. For water, our phases of matter, we have ice. Ice is really cold, it's the lowest temperature. If you heat up ice, eventually it becomes liquid water. If you heat up your liquid water enough, it starts bubbling, it starts boiling, and then it turns into gaseous vapor and maybe condenses on your windows, especially if it's the winter. But it turns into a gas because you've added a lot more energy, heat into it. There are other phases of matter, we aren't going to talk about them. So solid matter. In solid matter, our atoms and molecules, whichever we have, are packed close together. I often call this touchingly close. They can interact with their neighbors. And they're in fixed locations. The atoms and molecules can vibrate in their little fixed position, but they do not move past, they do not move around or past each other. So they are locked into their little seat. Because of these properties, a solid has a fixed volume. There's no empty space. You can't condense it. So you can't squeeze the particles closer together. They're already touchingly close. And it also has a rigid shape because they can't move around or past each other. They can't move past their neighbor like leapfrogging over each other. So it's got a rigid shape. So characteristics of a solid, fixed volume, and a rigid shape. And an analogy for this is students during lecture or people at a movie theater. If you go to a movie, sometimes you have assigned seats, that's cool. Generally, everyone crowds in, assuming that it's a packed movie theater, everyone sits in a spot, and then the movie happens, and then you get up from your spot, and then you leave. During the movie, you're not swapping spots with your neighbors, right? That's not a normal thing that people do at movie theaters. There's not like all right, now we're going to musical chairs. during, like there's not an intermission where you play musical chairs. Everyone's stuck in their seats for the duration of the theater. There's also not really empty space. There's not like, hey, let's fit 5 more people in here in these like between the seat spaces. Everyone's stuck in their spot. But you can still drink your popcorn and eat your snacks, right? When you're at the movie theater. You can wiggle around. You can chit-chat with your neighbor. You can share. I love that scene, stuff like that. So people at a movie is like our solid state. Our solid matter can also be further described as crystalline. Crystalline forms, you guessed it, crystals. So think of anything that forms crystals, like diamonds, or quartz, or salt, or sugar. Anything that forms crystals, it's crystalline. And what makes it crystalline is that there's long-range repeating order. So the arrangement of the particles repeats. If we had a full class, the class would be roughly crystalline. If we look at the desks, right, the positioning of the desks, if we took a picture, roughly, like from the roof, from the ceiling, of this one section, we got like 9 desks, we could overlap that. We could take a picture of another section of desks, and if we overlap the two, they would probably overlap pretty well. And that's what happens with our crystalline solids. If you zoomed way in and you took a picture, and then you zoomed way into a different spot and you took a picture, and you overlap those 2 sections, they should overlap. It should become they're the same picture sort of moment. Because the way that they're structured repeats over and over again. So you should be able to get different sections to overlap. Other solids are amorphous. They're sort of blobby. So they don't have long-range repeating order. If you did the same thing, if you zoomed way in and you took a picture of what does the chemical look like, and then you took a different section, you zoomed way in, and you took a picture, and you tried to get those 2 images to overlap, you'd have a really tough time getting those 2 things to overlap because they're not repeating the same order over and over again. So glass and plastic are examples of amorphous solids. They don't have long-range repeating order. The crystalline version of glass is quartz, depending on the type of glass, depending on the type of quartz. This would also be similar to kindergartners on the floor for story time. You probably wouldn't get a nice, even arrangement of students because they're kindergartners. That's our solid matter. In liquid matter, the atoms and molecules are about as closely as they do in solid matter, still touchingly close. However, in liquid, they are free to move relative to each other. Can move past / around each other. So they can exchange spots with their neighbors. But again, they're touchingly close. Because they're touchingly close, it's got a fixed volume. You can't compress it. There's no empty space. They've already taken up the minimum amount of space that they can. But because they can move past and around each other, they do not have a fixed shape. So that's why when you spill water on your desk or elsewhere, right, it spreads out, it moves, it slides, it glides, all that good stuff. And that ability to flow is what makes them assume the shape of their container. The analogy that we've got in here is students during lab period. During lab period, generally, we've got the maximum amount of students, depending on the semester, and you can swap places with your neighbor. It's not like in lecture where it would be weird if 2 of you just got up and swapped places and sat down. In lab, that wouldn't be that weird of a thing. Happens all the time. The analogy that I like to use is people at the front of the concert, or at the front of a concert. right? If we go see William Eyelash in concert, up in the front, I'm assuming, I've never been to see Billy, but I'm assuming that the front is just absolutely jam-packed with people. I've been to a couple of concerts. Usually the front is pretty jam-packed, right? People are trying to get as close as they can to whoever's performing on stage so that they get the best view, they get the best pictures, they get the best experience. Maybe they get a high five or some other fun stuff. So this is like people at the front of a concert. If you go up, if you try to get in there, right, they are packed in tight. Good luck trying to get in there. But they can switch places with each other. If you've got two besties up in the front, right, they might switch places, take turns getting the front position. If somebody needs to go to the bathroom, they can escape. You can get out. Good luck getting back in, right? So that's our liquid matter. And then we have gaseous matter, or gases. So in our gases, there's a lot of space. So this is our first, our only one that's not touchingly close. There is empty space between our particles, and they are free to move relative to one another because they're not touchingly close. Because of these, gas can be compressed. So when you compress something, you reduce the amount of empty space. If you try to compress a solid or a liquid, usually doesn't go very well. You're either going to break whatever you're using to try to compress it, or other bad things will happen. An example of this, if you take one of those $1 water bottles, hopefully they're still $1, plastic water bottle, if you try to squeeze it while it's completely full, what happens? It either breaks and water sprays everywhere because your container has broken, or you just get tired from trying to squeeze something that can't be compressed. However, if you drink all the water first, now it's full of air, and you can twist it, you can squeeze it, you can do whatever you want, you can twist it up a lot, and then flick off the lid and it goes flying into the air, into your friend's butt, wherever you intend to shoot it. Because gas is compressible, liquid is not compressible. This is also why they use liquids for hydraulic presses, because they're not compressible. Our analogy here is people when class is over. When class is over, we all funnel through that little doorway, and then you all spread out and do your own thing, right? We don't all just like stay in a clump, a tight little clump, walking around campus to our next thing. That would be really funny to do, I feel like. We're not going to do it. It would be really funny to me, but that would be if we were a liquid, right? Because then we'd be moving around. Unless we were really strict, like a marching band, then it'd maybe be more like a solid. Okay. Questions about our phases? Solid, liquid, gas. Okay, moving on to composition. We can also classify based on our composition. Our matter is either made up of elements, it's made up of compounds, or it's made up of mixtures. We've got this flowchart from the book. There's a lot of nice diagrams in the book that you can refer to. The first way that we are going to divide our material, our matter, is that we've either got pure substances. Pure substance, just one thing or one type of thing. It's only that one thing. That's what makes it a pure substance. It's not a corrupted substance. It's not an impure substance. It's a pure substance. It's just one thing. It's not like saying it's a holy substance either. And then we also have mixtures. 2+ things. It's at least two things that are together. They're mixed. That's what makes it a mixture. So that's the first way that we are going to divide our matter. Pure substance or mixture. Our pure substances we can further subdivide. So we can categorize them into two different types. We've got elements and we've got compounds. So an element cannot be broken down. It's as simple as it gets. It's any of the boxes on the periodic table. Each and every one of those boxes is a different element. Some of them don't exist right now that we know of. So any of these boxes on our periodic table in class, each of these, all 118 possible options that we know about for elements. So any of those, if you've just got that thing, that's a pure substance and it's an element. A compound is what most things are. Most things are a compound. It's two or more elements, and they have fixed, meaning you're not changing them, definite proportions. So it's always a ratio of a certain number of one element to a certain number of another element. Like how water is 1 oxygen, 2 hydrogens. Water is always going to be 1 oxygen, 2 hydrogens. It's never going to be something else. And that is a compound. It's still a pure substance since it's just that one compound. Our mixtures, on the other hand, we can categorize as either heterogeneous or homogeneous. So we've got different prefixes here referring to how well mixed they are. So heterogeneous mixtures. Hetero meaning, I think, other or different. So the composition varies from one region of the mixture to another. So it's not smoothly or evenly mixed. It's still made of multiple substances, and usually you can see that there's different substances. So anything where there's two different things and you can tell that there's two different things, like if you mixed salt and sand, assuming that it's white salt, assuming that it's sand-colored sand, right? If you mix the two together, you'd notice there's stuff in there that's white, there's stuff in there that's tan, or maybe it's black sand, right? You'd notice that there's two different colors in there, and you would know that it's not smoothly mixed. That's a heterogeneous mixture. Or like a vinaigrette salad dressing. Something that you have to shake it before you apply it to your salad, otherwise you just get like a lot of oil. And that can be a thing, but usually not what you're expecting when you're trying to get salad dressing. So something that often forms layers for heterogeneous mixtures. For homogeneous mixtures, homo meaning same, so it's the same consistency throughout. Like peanut butter, Pepsi, Dr. Pepper, ranch dressing, sort of. Some soups, water, sweetened tea. Things where if you take a sample from one section, it should be the same as a sample from another section. So the homogeneous mixtures have uniform compositions, even compositions throughout, because they mix uniformly, they mix evenly. So you don't necessarily have to shake them before you apply them. In the case of condiments. All right, let's test our knowledge. In these images, a blue circle represents an atom of one type of element, and red square is a second type of element. Which of these images is a pure substance? The correct answer is A. It's A because we've got one red with one blue, not in that order, together for each of these. Right? We've got a compound that's made up of one blue, one red together, and that's all that we have there. Only this one unit just repeated. In B, we've got a mixture because we've got blue circles and red squares, but they're somewhat evenly distributed. This would probably be a homogeneous mixture. And in C, we've got a heterogeneous mixture. It is not really mixed at all, or it's not uniformly mixed. They're together, they're just not nice and evenly distributed. Questions about anything we've talked about in Chapter 1 so far? Cool, then we will stop there for today.